Hello my geniuses, welcome to another biochemical lecture series today. It's your great sciences of Lorenzo, and we'll be talking about special pathways of fatty acid oxidation. Okay, the special pathway of fatty acid oxidation. In our last video, we'll talk about beta oxidation of long chain fatty acids, where we'll talk about the activation step, the transport step, and the beta oxidation proper. Then I ended it with the regulation of beta oxidation. So in this video, I'll be talking about special pathways of fatty acid oxidation, the pathways that are not like the regular beta oxidation pathway. So here we'll be talking about beta oxidation of all chain fatty acid, beta oxidation of very long chain fatty acid, alpha oxidation, and omega oxidation. All these things appear it into one single special pathways of fatty acid oxidation. I get it now, because the natural one in which the body uses constantly is the beta oxidation of long chain fatty acid, because we eat what palmitic acid. Palmitic acid is the normal fatty acid our body know, carbon 16. So apart from palmitic acid, you want to talk about the very long chain, the odd chain, the medium chain, the alpha, and the omega oxidation, all of them in this video. Okay, now so if you are new to my channel, make sure to subscribe and turn on your post notification button so that anytime I drop any video, you'll be sure to be notified. If you want me to make a video for you, drop it down in the comment section. I promise I'll make that video for you. So if you know any medical student that will need this video, especially those in their preclinical classes, please send this video to them. You'll be doing them a great service, and don't forget that. So let us jump right into the video. We will first start with the question: what is fatty acid oxidation? What is fatty acid oxidation? We'll call it oxidation of fatty acid. I get him now. So fatty acid, remember, fatty acid is a product when triacylglycerol is broken down to form glycerol and fatty acid in lipolysis. So during lipolysis, what happens in the liver? The body breaks down, in the help of what, glucagon and catecholamine, the body breaks down what we call triacylglycerol, which is TAG, into what? 2 moles of fatty acid, MAG, and glycerol. So that fatty acid is transported to the liver by what we call albumin. When it's transported by albumin, it's transported to what? To help to convert it into what? ATP. Okay, now so the conversion and the oxidation of fatty acid to give what? Acetyl-CoA, which is used to produce ATP, is called what? Fatty acid oxidation, or we'll call it oxidation of fatty acid. So when we convert fatty acid by oxidation to give us what? Acetyl-CoA, or let's say intermediate of TCA that is used to make ATP. We call it what? Fatty acid what? Oxidation. You get it now? So conversion of fatty acid that was mobilized from lipolysis for it to be used to convert and to form ATP that we use as an energy source. We call it what? Oxidation of fatty acid. And the most important oxidation of fatty acid is using beta oxidation process. So the beta oxidation process is the one that is widely used, but we also have alpha oxidation and omega oxidation, which I'll be talking about in this video. You get it now? So apart from beta oxidation, we also have different pathways. We have omega medium chain fatty acid, we have very long chain fatty acid, so many fatty acid oxidation steps which we'll be talking about. I get it now? So some fatty acids are different. You have the one that is long chain, you have the very long chain, we have medium chain, we have odd chain, we have even. All of them are just different based on their carbon number of their carbons there. You get it now? So now in this one we are just talking about the special ones, not really it's same thing. Some of them occurs as beta oxidation, but this one are people that are not just in the usual step. They occurs once in a while when the enzymes that are used to break them down are available. So the next question we'll ask ourselves: why special pathways are needed? Why are they needed in the body? Number one, because of structural variation. Structural what? Variation. I get them now. So naturally we're supposed to have what we call even chain. We have to what we call long chain fatty acid. The body already know long chain fatty acid, breakdown of long chain fatty acid. But what if you have odd chain, or you have branch, or you have very long chain, something that the body doesn't know, and the body doesn't have enzyme to break down? So what will you do? You get it now? So you understand what I'm saying? So naturally your body has enzyme to break what? Very long chain fatty acid. So since your body have an enzyme to break long chain fatty acid, but do not have an enzyme to break odd chain fatty acid, branch chain fatty acid, very long chain fatty acid, medium chain, alpha chain, not that they don't have it, but these enzymes are scarce and they only come when they are needed. Okay, now, so that due to structural variation, that is number one. Two, defect in beta oxidation enzyme. When there's defect in any of the beta oxidation enzyme, like deficiency in fatty acid synthetase or deficiency in carnitine, any of these enzymes, if they are absent, your body switch to use what? Alpha oxidation and omega oxidation, medium chain fatty acid, any of them, your body will switch. And also, why is it needed? Because of toxic accumulation of fatty acid if not metabolized. So if there's accumulation of fatty acid in the body will switch to use special active, the body will switch to use switch to use special pathways for beta oxidation. Okay, now the body will switch to use special pathways for fatty acid oxidation if there's accumulation of fatty acid. So if there's accumulation of fatty acid greater than the normal one where the body can break down, your body will switch to another special pathway it will use. So number one, because of structural variation. Two, because of any defect in any enzyme in beta oxidation. The next one is what? When there's toxic accumulation of fatty acid. And the last one is efficiently utilization of all fatty acid to convert them to ATP. So ATP is very, very important. So we need ATP here for energy production. So ATP is used for energy production. If there's no ATP, what happens? The body cannot have energy, and energy is used to drive the muscle cells. You get it now? So energy is used to drive the muscle cells. So where energy is absent, what happens? The body will be dormant and it will not be able to move. You get it now? So I'm giving you the reason why we call it special. Why is it called special? It's called special because it is used to substitute for beta oxidation. So not that most of them are say beta oxidation, it's just that this part are substitution points in which they use in case the normal enzyme we know for long chain fatty acid, if the normal enzymes are absent, my body switch to use this one here. So the next question here is that what are the importance of special pathways? Why are they important in the body? Number one, to prevent accumulation of what? Unused or toxic fatty acid. To prevent accumulation. So when there's accumulation of normal fatty acid, what happens? The body switch to special pathways so that they can also be oxidized to produce intermediate of what? TCA, for the purpose of what? Energy production. So the body uses it for one, to prevent accumulation of unusual or toxic fatty acid. That is number one. Two, to provide alternative route for energy production. It's not only the usual beta oxidation the body know. The body is just trying to produce another route whereby energy can be formed also, not even the normal pathway. The next one, also to protect the cell and tissue from what? Lipid toxicity. Because when there's lipid toxicity, what happens? There will be what? Oxidation by acid radicals, and when there's oxidation by acid radicals, it will lead to inflammation. Leading to inflammation, the fatty droplet will be dropped in the blood vessel, causing atherosclerotic plaque, causing obesity, causing vasodilation of the blood vessel, destroying the body, and sometimes promoting death. So that's why it prevents the body from what? Lipid toxicity, and also generate what? Important intermediate of TCA and glycolysis. So that is also to provide and to produce intermediate of TCA and glycolysis. So when you are producing intermediate of TCA, what happens? It is shunted into the TCA cycle to produce what? ATP. And the last one, to maintain normal lipid homeostasis. So now, if you want to maintain lipid homeostasis in the sense that when you increase lipid, what happens? Your body tends to break them down so that they can be reduced, because a high amount of lipid will cause you what? Hyperlipidemia. And hyperlipidemia can lead to various pathological symptoms. I get it now? Various pathological symptoms which can be harmful to the body. Okay, now, so we know the introduction, we know why they are called special, I get it, and why they are needed, and the last one is the importance of special pathways for fatty acid oxidation. So now, what are these fatty oxidation? Where can we group them into? Are you getting now? Number one, we'll be talking about the beta oxidation of short chain fatty acid. Talk about the beta oxidation of very long chain fatty acid. We'll talk about alpha oxidation and what? Omega oxidation. Also, if we can add to medium chain fatty acid, we'll also add medium chain fatty acid here. So all, I'm just pairing them in one because I don't want to do it in separate video. Separate video will make them to be short, and if they are short, you might not be able to watch. So I want to elaborate them and make them very easy, break them down for you to understand. So we'll be starting with the first one, beta oxidation of short chain fatty acid. Hope you are still with me. Beta oxidation of short chain fatty acid. Beta-oxidation of all chain fatty acid is the what oxidation of all chain fatty acid for the production of what Succinyl-CoA. Are you getting that? So we are trying to break down all chain fatty acid. When we oxidize them, the goal is to produce what Succinyl-CoA. Succinyl-CoA is an intermediate of TCA cycle which enters in a TCA cycle to produce what ATP for us. Are you getting that? So here in all chain fatty acid, we want to produce Succinyl-CoA as the end product. While in normal beta-oxidation of long chain fatty acid using palmitic acid, the goal there is to make what we call 8 moles of acetyl-CoA. So we are also making an intermediate of TCA cycle. For beta-oxidation of long chain fatty acid, which is palmitic acid, we are getting 8 moles of acetyl-CoA as the end product. But in the oxidation of all chain fatty acid, we are getting what Succinyl-CoA as the end product. Are you getting now? But we have a substrate. The substrate here is Propionyl-CoA. Propionyl-CoA is the substrate, while Succinyl-CoA is the end product. So the conversion of Propionyl-CoA to Succinyl-CoA, which enters into a TCA cycle, is called what? Oxidation of all chain fatty acid. And all this occur in what we call the mitochondrial matrix. So it occurs inside the mitochondrial matrix. Are you getting now? So if you are to look at the step one after the other, follow me. We have defined it that beta-oxidation of all chain fatty acid is the breakdown of what all chain called Propionyl-CoA to form Succinyl-CoA, which is an intermediate of TCA cycle, which enters into the electron transport chain for the production of what ATP. And where does it occur? In the mitochondrial matrix. So now in the biochemical pathway, now the first step we'll be going to is what we call carboxylation reaction. So we want to add CO2 here. Are you getting that? Carboxylation reaction, which is the addition of what CO2. So now what happens? Propionyl-CoA is formed by the acetylation of propionic acid. So when we acetylate propionic acid, which means adding acetyl-CoA to propionic acid. So if we add acetyl-CoA plus propionic acid, we'll be getting what we call Propionyl-CoA. Are you getting now? And with Propionyl-CoA, first of all, we add CO2 to Propionyl-CoA to the enzyme Propionyl-CoA carboxylase. You get it now? Again, Propionyl-CoA is carboxylated with CO2 by the enzyme Propionyl-CoA carboxylase to form what? D-methylmalonyl-CoA. You get it now? But I also said that Propionyl-CoA is formed by the acetylation of what? Propionic acid. So we are adding propionic acid, which is 3 carbons of fatty acid plus acetyl-CoA. Are you getting now? So when we add it, we now get what we call Propionyl-CoA. And the same Propionyl-CoA is now added with CO2. So we are adding 1 carbon to Propionyl-CoA, which is Propionyl-CoA is 3 carbon now. Are you getting now? Propionyl-CoA is 3 carbon. So when we now add 1 carbon to it again, adding CO2 to it, we are getting D-methylmalonyl-CoA. If we get D-methylmalonyl-CoA, what happens now? By the enzyme Propionyl-CoA carboxylase, and anytime we are using the enzyme carboxylase, we'll be adding what? Biotin. So biotin will be used here, and in the presence of what? ATP. So biotin, which is a vitamin, will be used in this case too, which is a B complex vitamin. It will be used here, and when we use here, which is B7, remember. So when we use biotin help is a coenzyme in which we use in the carboxylation of Propionyl-CoA to form D-methylmalonyl-CoA. In step 2, are you getting now? We call it racemization. We are using the enzyme racemase. So now we are converting D-methylmalonyl-CoA to what? L-methylmalonyl-CoA by isomerization. So if we isomerize D-methylmalonyl-CoA to L-methylmalonyl-CoA, what happens? We are using the enzyme racemase. So racemase now is just like an optical isomerism, converting D optical isomer into L optical isomer. They are stereoisomer of themselves. So we are using racemase. Are you getting it? And racemic solution is a solution where you have D and L part of the isomer inside the same mixture. You get it now? So when we isomerize D-methylmalonyl-CoA to L-methylmalonyl-CoA, we are using the enzyme racemase. The first one is what? Propionyl-CoA is carboxylated by Propionyl-CoA carboxylase to form D-methylmalonyl-CoA in the presence of ATP and biotin. Then now, for D-methylmalonyl-CoA, what happens? We isomerize it to form L-methylmalonyl-CoA using the enzyme racemase. Now, what do we now do now? We did something now. The L-methylmalonyl-CoA, what happens? We rearrange now. We rearrange the position of phosphate now. So what happens? The L-methylmalonyl-CoA is what? Converted into what? Succinyl-CoA. The L-methylmalonyl-CoA is converted to Succinyl-CoA by what we call the methylmalonyl-CoA mutase. So we are using a mutase enzyme here. So the mutase enzyme is used in the presence of also vitamin B12 to convert L-methylmalonyl-CoA to what? Succinyl-CoA. All these enzymes, they are just what? Isomerization enzyme. So they are just isomerase. Are you getting me? So they are isomerase. So the first one we used was racemase, followed by what? Mutase. So here in the mutase, we are converting it here from L-methylmalonyl-CoA to what? Succinyl-CoA. Again, now in the presence of what? Vitamin B12. Now the Succinyl-CoA is donated into the TCA cycle. So when it's donated into the TCA cycle, what happens? It is used to make what? ATP. Don't forget, it's used to make what? ATP. The clinical scenario we'll be talking about here is the propionic acidemia. This propionic acidemia is deficiency in what they call propionyl-CoA carboxylase. Propionyl-CoA carboxylase is the what? Conversion or the carboxylation of propionyl-CoA to d-methylmalonyl-CoA in the presence of ATP and biotin. So when this enzyme is absent, there will be accumulation of propionic acid. And propionic acid is converted to form propionyl-CoA by the acetylation with acetyl-CoA. So when acetyl-CoA condenses with carbon-3 fatty acid, which is propionic acid, it forms propionyl-CoA. Propionyl-CoA will now be carboxylated to form d-methylmalonyl-CoA. So when the enzyme is absent, you'll be accumulating propionyl-CoA and propionic acid too. So that will now form what we call, they to be high in the blood, causing propionic acidemia. So now what will be the metabolic field? Due to the presence of acid in the blood, the patient will be having what we call metabolic acidosis. And when there's metabolic acidosis, what happens? There will be vomiting. There will be nausea and vomiting. There will be hyperammonemia in the blood also, because the blood will be high with ammonia. And there will be developmental development, because there will be developmental delay in the child, because due to hyperammonemia, there will be what? Mental retardation. The brain will not form very well. Sometimes the brain will swell. There will be too many neural delay in the child, because it always happens in the child. So if there is what propionic acidemia, it will really greatly affect the central nervous system. So remember, metabolic acidosis, what happens? We have vomiting, we have hyperammonemia, we have developmental delay. The next one is methylmalonic acidemia. Now when there's methylmalonic acidemia is when there's deficiency of methylmalonyl-CoA mutase. When there's deficiency of methylmalonyl-CoA mutase, there will be increase in d-methylmalonyl and L-methylmalonyl. So there will be increase in methylmalonyl-CoA. There will be increase in methylmalonyl-CoA, and if there's increase in d-methylmalonyl-CoA and L-methylmalonyl-CoA, what happens? Now, what will happen to the patient? One, the patient will have what we call neurological deficits. And if the patient has neurological deficit, due to increase in this acid, the patient will be metabolic acidotic. And I get it now. There will also be hyperammonemia. There will be failure to thrive, and there will be developmental delay. Why? Because there is an increase in what? Neural defects. I get it now. There's an increase in neural defects. Don't forget. So the next one we'll be going to, we are done with oxidation of all-chain fatty acid. So the next one is beta oxidation of very long-chain fatty acid. I've taught you the one of long-chain fatty acid. I've taught you the one of all-chain fatty acid. So we are in very long-chain fatty acid. So when the carbon atom is greater than 22, when the carbon atom is greater than 10, we call it very long-chain fatty acid. So any carbon atom greater than 22 is already regarded as long-chain fatty acid. 20 is right. There's still 20 chain fatty acid, which is arachidonic acid. Are you getting now? So you still have propionic acid, which is 3. You still have stearic acid. We have palmitic acid. You have oleic acid, you have linoleic acid. All of them, they are still within the range of less than 20 carbon atom. So when it is not greater than 22, what happens? We call it very long chain fatty acid. And this beta oxidation occurs inside the peroxisome. Are you getting now? Inside the peroxisome, very long chain fatty acid is oxidized inside the peroxisome. Are you getting now? So because the body do not have it doesn't occur in the mitochondrial matrix, because the mitochondrial matrix do not have specific enzyme to what? Oxidize very long chain fatty acid, which means the enzymes that are required are present in the peroxisome. If this very long chain, the enzyme do not bring them down, there will be accumulation of very long chain fatty acid. There will be, which we'll be talking about their clinical scenario in the later part of the video. So remember, site, where does it occur? Peroxisome of the liver and the kidney. That is where it occurs. The peroxisome of the liver and the kidney. The next one is the biochemical pathway of the beta oxidation of very long chain fatty acid. The first one now is activation. I get it now. The first one is activation. Now remember, and in the activation step, first of all, we want to what? Convert very long chain fatty acid into what? Very long chain fatty acid CoA. This first one. First of all, converting fatty acid to what? An acetylated version by adding what? CoA to it. So very long chain fatty acid is acetylated, which means it will join acetyl-CoA by what? Acetyl-CoA synthesis. So acetyl-CoA synthesis, the synthesis part there is using ATP. So when we are to what? Activate very long chain fatty acid by what? Adding ATP to it. So when we condense ATP to it to form ADP, what happens? We are converting it from very long chain fatty acid to what? Very long chain fatty acetyl-CoA by acetyl-CoA what? Synthesis. So we have added CoA to it. Before, it doesn't have CoA. I get him now. So we now add CoA to it. So any fatty acid greater than 22, what happens? First of all, we would add what? Acetyl-CoA to it. So when we add acetyl-CoA by the enzyme acetyl-CoA synthesis using ATP, what happens? If we use ATP, we get what? Very long chain fatty acetyl-CoA. Now if we get very long chain fatty acetyl-CoA, what happens? Oxidation will occur in the peroxisome now. So how will oxidation occur in the peroxisome? The very long chain fatty acetyl-CoA will be oxidized by what we call acetyl-CoA oxidase. Again, the very long chain fatty acetyl-CoA will enter into the peroxisome. When they go there, what happens? They will be oxidized by acetyl-CoA oxidase. The acetyl-CoA oxidase will form what we call trans-2-enol-CoA. I get them now. Trans-2-enol-CoA, where you have shortened, where it is shortened by what? 2 carbon. When it is shortened by 2 carbon, it will now form what we call hydrogen peroxide plus the shortened part of what? Fatty acetyl-CoA. Again, I told you that the very long chain fatty acetyl-CoA in the peroxisome will be oxidized to what? Trans-2-enol-CoA, which shortened by what? 2 carbon. So now it is shortened by 2 carbon. What happens? It will now become what we call hydrogen peroxide plus the shortened form of fatty acetyl-CoA. So we splitted it again in the peroxisome. So the enzyme that catalyzes is what? Acetyl-CoA oxidase. The acetyl-CoA oxidase remove 2 hydrogen atom from the fatty, very long chain fatty acetyl-CoA to form what we call a trans-2-enol-CoA. And when it forms a trans-2-enol-CoA, it will also give off hydrogen peroxide. Don't forget it. Now the hydrogen peroxide, now what will happen? It will be broken down by catalyst to form what we call 2 molecules of water plus oxygen. 2 molecules plus water plus oxygen. Now catalyst breaks down 2 moles of hydrogen peroxide giving off in the peroxisome to form what? 2 molecules of water and what? Oxygen. Okay, now so now what will now happen? Now the shorting part, because in the very long chain fatty acid, all we needed is to break it down into 2 molecule shots. That's what we need. 2 molecule shots and what? Peroxide. So the shorting part of what? Fatty acetyl-CoA, because it was very long chain fatty acetyl-CoA. So now it is very long chain fatty acetyl-CoA. I now use what we call oxidase to break it down. We're removing what? 2 molecule shot. It is the 2 molecule shot I'll be using in this case. The 2 molecule shot and hydrogen peroxide. The hydrogen peroxide give off water and CO2 and oxygen, while the shortened fatty acetyl-CoA is transported to the mitochondria for what? Further beta oxidation to produce what? Acetyl-CoA. When it produces acetyl-CoA, it also produces what we call Propionyl-CoA. Are you getting it? Don't forget. In the clinical correlation, we have Zellweger syndrome. We have Zellweger syndrome and X-linked Adrenoleukodystrophy. Zellweger syndrome and Adrenoleukodystrophy. So what is Zellweger syndrome? Zellweger syndrome is when there's deficiency in what we call peroxisome biogenesis. Biogenesis. So when there's deficiency in peroxisome biogenesis, which means there's an issue or there's destruction in the peroxisome. So the peroxisome is not present or is not active in the cell. So when there's absence of peroxisome, what happens? There will be accumulation of very long chain fatty acid. Are you getting me? There will be accumulation of very long chain fatty acid, because in the peroxisome, that is where very long chain fatty acid CoA is what? Oxidized. So when there's no peroxisome, what happens? There will be accumulation of very long chain fatty acid, because they will not be oxidized to form what? Shortened part of trans-2-enol-CoA, and also it will not form what we call hydrogen peroxide. You get it now? So there will be accumulation of very long chain fatty acid. And when there's accumulation of very long chain fatty acid, it will give us what we call hepatosplenomegaly, because due to inability for the liver to metabolize them, they will accumulate in the liver, causing the liver to be big. Number 2, there will be what developmental delay, because the brain will not form properly. So when there's developmental delay, there will be neural deficit, there will be neurological deficit, and what we call hypotonia. So due to the neurological deficit affecting what we call the motor center of the brain, I get it now, there will be hypotonia. And when there's hypotonia, there will be flaccid paralysis, and so many things will occur. The next one is what we call X-linked adrenoleukodystrophy. Now, in the X-linked adrenoleukodystrophy, there's deficiency in what? The transport of very long chain fatty acid into the peroxisome. The first one is that there's an issue with the peroxisome. The second one, now, to transport the very long chain fatty acid CoA into the peroxisome. When there's an issue there, it will give you what we call X-linked adrenoleukodystrophy. Are you getting me now? First of all, remember, after they have been acetylated with acetyl-CoA, are you getting me now, to form very long chain fatty acid CoA. Very long chain fatty acid CoA, they are not transported into the peroxisome where they are oxidized. So when that transport is absent, what happens? Now, what happens? It will what causes what we call adrenal insufficiency, because there will be accumulation of very long chain fatty acid in the adrenal gland and the nervous system. So when there is accumulation, it will cause what? Adrenal insufficiency, which means your adrenal gland will not be producing any hormones in the cortex and in the medulla. Also, there will be hearing impairment too. There will be hearing impairment, there will be vision impairment, and there will be progressive neurological deterioration. This will greatly affect the brain. You get it now, and also the adrenal glands. So I hope this is making sense to you. So we have talked about the beta-oxidation of short chain fatty acid, and we have talked about beta-oxidation of very long chain fatty acid. So short chain fatty acid, very long chain fatty acid, and in my former video we talked about long chain fatty acid. The next we'll be talking about is alpha oxidation of branch chain fatty acid. So we have talked about beta-oxidation of short chain, we have talked about beta-oxidation of very long chain fatty acid. So in this one we're talking about alpha oxidation of branch chain fatty acid. This one is not a linear chain now, these are branch chain fatty acid. So example of branch chain fatty acid is Phytanic acid. Phytanic acid cannot be broken down by beta oxidation. It cannot undergo beta oxidation because there's a methyl group on the beta carbon. So since there's a methyl group on the beta carbon, it will undergo what we call alpha oxidation. And if you undergo alpha oxidation, where will this occur? It will occur in the peroxisome. In the peroxisome, it will occur there to form what we call Phytanic acid. After formation of Phytanic acid, it can now undergo beta oxidation. So not that it will not undergo beta oxidation, it will still undergo beta oxidation, but it has to form a carbon that it will be easier for it to undergo. Next is the biochemical pathway of alpha oxidation of branch chain fatty acid. Now remember, we say the first of all is the activation step. The Phytanic acid will be acetylated with acetyl group or condensed with acetyl-CoA to form Phytanol-CoA. By Phytanol-CoA synthesis in the presence of ATP. Now you now have Phytanol-CoA now. Now you have Phytanol-CoA. What is the next thing? Are you getting me now? You now add OH. You have add what we call hydroxy group to the process of hydroxylation. So when we add hydroxy group there by adding OH to the Phytanol-CoA, we will now form what we call alpha hydroxyl Phytanol-CoA. Alpha hydroxyl Phytanol-CoA. We are adding hydroxy group by adding OH. Now using in the presence of oxygen, and also using what we call iron 2, which is the cofactor. We are using iron 2 as the cofactor here. So since we are using iron 2 as the cofactor and we are oxidizing it by adding OH to it, by adding OH to the Phytanol-CoA to form alpha hydroxy Phytanol-CoA. Are you getting now? So ordinary Phytanol-CoA, it has oxylated to alpha hydroxy Phytanol-CoA. Now when we have oxidized it, now we are using the enzyme Phytanol-CoA hydroxylase. So the first reaction, we activated it by adding acetyl-CoA by Phytanol-CoA synthesis. The next one is that we hydrolyze the Phytanol-CoA to form alpha hydroxy Phytanol-CoA in the presence of oxygen and iron 2. The next thing we now do, we now decarboxylate it now. Are you getting now? We remove carboxy group. We remove carboxy group from what we call alpha hydroxy Phytanol-CoA. If you remove CO2, you will now form what we call propanol. If you remove CO2 from alpha hydroxy Phytanyl-CoA, you produce what we call prestanal. So now we have formed prestanal. Follow me. The first one is activation by adding phytanic acid with acetyl-CoA to form what? Phytanyl-CoA in the presence of what? ATP. The next we now add OH to it, which is by hydroxylation, adding OH to it to form what? Alpha hydroxy Phytanyl-CoA. The next one we now remove CO2 from there. So when we remove CO2, we now form prestanal. So now we have formed prestanal. What's the next thing now? So the prestanal now will now be oxidized. The prestanal will be oxidized. So if we oxidize prestanal, so it just like you remember alkana. So when we have alkana here, we have alkana is just like prestanal. So when we have prestanal, we now oxidize prestanal, we form what we call prestanic what? Acid. Same thing. You have what? Alkanol to alkana, alkana to alkanoic acid, just in your secondary school, which is your high school, when you did what? Chemistry there, which is organic chemistry. So when you oxidize alkanol, you get alkana, and when you oxidize alkana, you get alkanoic acid. The same thing here. When prestanal form prestanic acid through oxidation, remember that there will be reduction of vitamin B3, which is what? Niacin. So niacin, which is NAD plus to NADH, will be reduced. Now remember, I told you and I explained it that, take for instance, when you were using alcohol, your alcohol in your organic chemistry, when you oxidize ethanol, you get ethanol. Ethanol is the alkana part of it. But alkana is now oxidized from alkanoic acid. Same here too. When you oxidize prestanal, you get prestanic acid. By prestanal dehydrogenase, reducing what? NAD plus. You get it now. So after getting to prestanic acid, now prestanic acid will now undergo what we call beta oxidation. Remember, same thing I talked about when we did oxidation of very long chain fatty acid and oxidation of short chain fatty acid. Very long chain fatty acid is being what you reduce by beta oxidation to the same thing, but the only problem here is that it is done in the peroxisome. When it is done in the peroxisome, just like this one too, because this is alpha oxidation of branch chain fatty acid, which occurs in the peroxisome. But remember, no matter how you undergo alpha oxidation, you will always still come back to beta oxidation. So because the body has special enzyme to carry out beta oxidation, so after alpha oxidation occur, there will be what? Beta oxidation. And alpha oxidation only occur when there is a deficiency or there's a reduction in beta oxidation. Are you getting that? So when the enzyme in beta oxidation, or it is not a long chain fatty acid, or at least not a long chain fatty acid or an short chain fatty acid. If it is a very long chain, a branch chain, or there's a difference in the configuration of the carbon in the fatty acid, it will not go by a normal beta oxidation. It will have to undergo omega oxidation or alpha oxidation before it undergo beta oxidation. So when I undergo beta oxidation using prestanic acid, I'll get what? Acetyl-CoA and what we call Propionyl-CoA. I'll get acetyl-CoA and Propionyl-CoA. So acetyl-CoA and Propionyl-CoA. Acetyl-CoA is an intermediate of TCA cycle, but Propionyl-CoA has to what? Undergo what we call beta oxidation of short chain fatty acid. So when you undergo beta oxidation of short chain fatty acid, you can now form what? Succinyl-CoA. So the end product here of acetyl-CoA is it entering into the TCA cycle, and the end product of Propionyl-CoA is it forming Succinyl-CoA, which is an intermediate of TCA. So remember, I said first of all, phytanic acid is being condensed with acetyl-CoA to form what? Phytanyl-CoA, using ATP and using Phytanyl-CoA synthetase. Then now we now give it OH. So when we hydrolyze it, what happens? It now become what? Alpha what? Hydroxyl Phytanyl-CoA. Then when I remove CO2, I put prestanal. Then when I now oxidize it, I form what? Prestanic acid. So prestanic acid undergo beta oxidation to form acetyl-CoA and what? Propionyl-CoA. Are you getting now? So remember, we cannot do beta oxidation because methyl group is added to the what? Beta carbon. So since methyl group is added there, you cannot undergo beta oxidation, and it occurs in the peroxisome, which is alpha oxidation occurs in the peroxisome, and the end product is what? Prestanic what? Acid. So the clinical correlation here is Refsum disease. So don't forget Refsum. It's a very, very important clinical correlation you should always what? Remember. So in Refsum disease here, there's deficiency in what? Phytanyl-CoA hydrolase. There's deficiency of Phytanyl-CoA hydrolase. So Phytanyl-CoA hydrolase is the one that what hydrolyzed, which it gives OH to what we call Phytanyl-CoA. When you add OH to Phytanyl-CoA, it will form what? Alpha hydroxy Phytanyl-CoA. Alpha hydroxy Phytanyl-CoA. So when you form alpha hydroxy Phytanyl-CoA, you can now decarboxylate it. When the enzyme is absent, what happens? There will be accumulation of Phytanic acid, because Phytanic acid condenses with acetyl-CoA. So when the enzymes are not there, there will be retrograding of the pathway, whereby increasing what? Phytanic acid. And when Phytanic acid build up in the nerve, what happens? It will cause peripheral neuropathy. Peripheral neuropathy will be there present. There will be what? Muscle weakness, because when there's peripheral neuropathy, there will not be neuromuscular transmission from there. There will be muscle weakness. Also, it will affect the vestibulocochlear nerve, causing hearing loss. It will affect also the ascending pathway that goes into the cerebellum, and also damage the cerebellar nucleus and lead to nerves that are present in the cerebellum, also causing cerebellar ataxia, giving you some cerebellar symptoms. Also, it form what? Retinitis pigmentosa, which is the pigment deposit in your retina. Besides the color, the eye color will change. Yeah. So one important thing you have to know, that Phytanic acid is a branching fatty acid, which cannot undergo beta oxidation like that. It has to undergo alpha oxidation first in the peroxisome, and when you undergo alpha oxidation in the peroxisome, it will not later undergo beta oxidation. Are you getting me? Very, very important. So we are done with our what? Alpha oxidation of branching fatty acid. So the last but not the least we'll be talking about is what? Omega oxidation. Are you getting me? Omega oxidation is very, very important for you to know this. Now, when I told you, when beta oxidation cannot occur, either beta oxidation enzymes are deficient there, or there's mutation in enzyme that codes for any of the enzyme in beta oxidation, or there is what? Overwhelm. Maybe beta oxidation is occurring too fast and the body's ATP level is dropping because there's all malfunctioning of beta oxidation. The body switch to alpha oxidation or omega oxidation, especially omega oxidation, because alpha oxidation also occur when it is only branching fatty acid. But in omega oxidation, when there's deficient in any of the enzyme, or beta oxidation is overwhelmed, we do omega oxidation. And in omega oxidation, this oxidation occurs in the what? Omega end of the fatty acid. And in the omega end of the fatty acid, there's a methyl group there. There's a methyl group in the omega end of the what? Fatty acid. So that is where oxidation will occur. Where the site where omega oxidation occurs, it occurs in the smooth endoplasmic reticulum of the liver and the kidney, and it also occurs in the peroxisome. The smooth endoplasmic reticulum of the liver and the kidney, and also the peroxisome. And now, what is the key point you have to know here? It occurs when beta oxidation is impaired, always, and also it occurs at the omega end of the fatty acid, where there's a methyl group attached, and the byproduct, which is the last product of it here, is dicarboxylic fatty acid. I get it. And I told you that dicarboxylic fatty acid can undergo beta oxidation. I get it. We can undergo beta oxidation to form what? At least ATP. I told you, it's just like a bypass mechanism. Here. So the goal here is to also produce ATP and the intermediate of what? TCA, which is Succinyl-CoA and what? Acetyl-CoA. But small amount of the dicarboxylic fatty acid enters into the urine and is being excreted. Are you getting that? So one thing you have to understand here is that the end product is dicarboxylic fatty acid, and it only occurs when beta oxidation is what? Affected. Are you getting that? So now you have to understand that in the biochemical pathway here, first of all, you are taking the omega fatty acid here. Now the omega fatty acid, which is at the omega end of the fatty acid, first of all, you add OH to it. You're hydrolyzing it now. Hydroxylation of what? Omega fatty acid now becomes what? Omega hydroxy fatty acid. Same thing I talked about in what? Alpha oxidation. In alpha oxidation, what do we do first? We first of all activate to form what? Phytanyl-CoA. Then when we activate to form Phytanyl-CoA, we now put what? OH with hydroxylation. I get it now. But here you are not what? You are not activating it first. There's already the fatty acid. You hydrolyze it. You put what? OH there. So when you put OH, you get what? Omega hydroxy fatty acid by the enzyme cytochrome P450. I get him now. So here, what are you doing? In cytochrome P450 oxygenase, monooxygenase, you are adding one oxygen. Here is oxygenation, not oxidation. You are oxygenating it here. By oxygenating it, you are adding 1 mole of oxygen here. When you add 1 mole of oxygen to the omega fatty acid, you'll be forming what? Omega hydroxy fatty acid. So cytochrome P450 monooxygenase is an enzyme that helps in detoxification and breakdown of harmful substances in the liver, converting them to what? Soluble form. So if you watch my BIC video on xenobiotics and process of detoxification and biotransformation, you see the function of what? Cytochrome P450 monooxygenase. So first one, you oxygenate omega fatty acid. When you oxygenate omega fatty acid, you get omega hydroxy fatty acid. So when you have oxygenated by cytochrome P450 monooxygenase, then you now do what? You now what? Oxidize now. You are doing oxidation. So when you oxidize omega hydroxy fatty acid, you get what? Omega aldehyde fatty acid. So anytime you are converting hydroxy group to aldehyde, remember, just the same way we have our ethanol now, ethanol to ethanoic acid, same way we are having here now. So the ethanol part of it, which is a carbonyl compound, is the aldehyde. So OH is representing 1 mole, which is ethanol. Are you getting now? So when you get omega hydroxy fatty acid, which is a compound of ethanol, which is an alkanol, what happens when you oxidize an alkanol? You get an alkanal. An alkanal is an aldehyde. So it's either you are getting an alkanal or you are getting an alkanone, so which they are carbonyl compounds. So are you getting now? So it's either it's having OH or it's having double O. Are you getting now? So OH means that there's 1 carbon, double bond going to O and a single bond going to H. Double bond going to O, single bond going to H. But if it's an alkanone, you are getting double bond going to O and another double bond going to O. 2 double bond going to what? Oxygen. But here now there's omega hydroxy fatty acid. In omega hydroxy fatty acid, which is an alkanol. So when you get an alkanol, what happens? Example, ethanol, what do you do? When you oxidize it immediately, you get what? Alkanal, which is a carbonyl compound. So same thing here. When we oxidize omega hydroxy fatty acid, we are getting what? Omega aldehyde fatty acid by alcohol dehydrogenase. So when you oxidize, what do you do to the cofactors? What do you do? What do you do to the coenzymes? You are what? Reducing from NAD plus to what? NADH. I get it now. So which means from here, at least you can get some molecules of ATP from here. Because the goal of this reaction is to make ATP when there is deficiency in what? Beta oxidation. So from here now, the NADH will now enter into the what? TCA circle to give what? 3 molecules of what? ATP. So I can also derive ATP from what? Omega oxidation too. So after getting omega aldehyde fatty acid, so what will I get? Again, I'll oxidize it again. So when I oxidize alkanal, which is a carbonyl compound, when you oxidize aldehyde or you cannot oxidize ketone. Yeah, you cannot oxidize alkanol. If you oxidize alkanol, it cannot be oxidized. But if you oxidize aldehyde, you can get what you call carboxylic groups. Are you getting now? So same thing you have here. When you oxidize omega aldehyde fatty acid, you get what? Dicarboxylic fatty acid. You get dicarboxylic what? Fatty acid. Same thing here. So which enzymes are you using? You are using what? Aldehyde dehydrogenase. Aldehyde what? Dehydrogenase, because this is a class 1 enzyme which is under oxidoreductase. So in oxidoreductase we have dehydrogenase, and dehydrogenase can undergo oxidation. It can undergo what? Reduction. Are you getting now? So one thing you have to know now, that here we are oxidizing. When we oxidize completely omega aldehyde fatty acid, we are getting what? Dicarboxylic fatty acid, thereby reducing NAD plus to NADH. So we have gotten 1 NADH from the step 2 and 1 NADH from the step 3, which all of them will enter into the electron transport chain to form what? ATP. Now we have the dicarboxylic fatty acid. We will now undergo beta oxidation, getting Succinyl-CoA and what? Acetyl-CoA. Are you getting now? So that's the end product from an intermediate of what? TCA. Acetyl-CoA is formed from a normal beta oxidation process of long chain fatty acids. 8 acetyl-CoA is formed from that when we are using what? Palmitic acid. But when you use short chain fatty acid, the goal is to form what? Succinyl-CoA. That's the goal, which we talked about in the beginning part of the video. But also short dicarboxylic acids are removed through the urine. Short dicarboxylic fatty acid. You get it now? Why the long dicarboxylic fatty acid undergoes what? Beta oxidation, why the short one is being urinated out. Are you getting now? They are broken down in the kidney and they are being urinated out. Remember, Anytime you are using cytochrome 450, you are trying to reduce the dangerous form, or you are trying to reduce the compound to a more soluble form, so you will be able to urinate it out. So most of all this dicarboxylic fatty acid has to be removed as urine, whilst the one that can be used to form ATP will be used to form ATP. So hope you understood this. So the key enzyme here is cytochrome P450 monooxygenase. Are you getting it? It's a very important enzyme that reduces the omega fatty acid to form ATP and also reduce it to soluble form so it can be urinated out. We also have alcohol dehydrogenase that would add OH there. Are you getting it? Alcohol dehydrogenase that oxidize omega hydroxy fatty acid to what? Omega aldehyde fatty acid. And we have aldehyde dehydrogenase that form what? Dicarboxylic fatty acid. So the clinical correlation here is dicarboxylic aciduria. Dicarboxylic aciduria. So when you have dicarboxylic aciduria, what happens? This is when there's increase in omega oxidation, when beta oxidation is defective. So take for instance now, your beta oxidation process is inhibited. Just for instance, maybe let's say carnitine deficiency. There's carnitine deficiency at this particular point. So if there is carnitine deficiency, or there is propionic aciduria, maybe your chain fatty acid cannot work, and there's Zellweger Syndrome or Adrenoleukodystrophy that is occurring, any of these particular pathway whereby beta oxidation cannot occur. When your body shifts to omega oxidation, excessive omega oxidation will cause what? Dicarboxylic aciduria. And when dicarboxylic aciduria come, you have now all your dicarboxylic acid will now be presented in the urine. Remember, I said only small amount of dicarboxylic acid is removed by the urine, but when they are not high, your ATP production is supposed to be high, but no, it will now start coming out from the urine. Are you getting now? So remember, you'll be hypoglycemic. Why will you be hypoglycemic? Because you are not forming intermediate of TCA that will undergo gluconeogenesis. Are you getting now? So you'll be hypoglycemic. You will undergo what we call muscle weakness. Muscle weakness will occur. Are you getting now? Because glucose is needed for ATP for the muscle. So when there's no glucose, there's no ATP. When there's no ATP, you'll be weak. Lethargy will occur, and there will be nausea and vomiting. The next one is MCAD, which is medium chain acyl dehydrogenase deficiency. Medium chain acyl dehydrogenase deficiency. So when medium chain fatty acid from fatty acid carbon C6 to about 10. So when they are being oxidized, when they are being oxidized, what happens? First of all, they undergo the fatty acid, first of all, condense with acetyl-CoA to form fatty acid-CoA. Then they don't need carnitine transport. They enter into the mitochondria. So when they enter into the mitochondria, the next one is that they are what? They are being oxidized. They are oxidized by what? Medium chain acyl dehydrogenase. So instead of them undergoing dehydrogenation reaction whereby they are oxidized, they cannot be oxidized because there's a deficiency in medium chain acyl dehydrogenase. Now remember, they're supposed to be oxidized to form what? Trans beta-2-enol-CoA, thereby reducing FAD plus to FADH2. But now if the enzymes is deficient at this particular case, do you know what will happen? There will be accumulation of medium chain fatty acid in the body, and when there's accumulation of medium chain fatty acid in the body, are you getting that? The body will rely on omega oxidation to undergo its pathway. So when there's deficiency in any of the pathway of beta oxidation, your body will rely on omega oxidation. So especially in MCAD, when medium chain fatty acid cannot be oxidized, the body will depend on what? Omega fatty acid for their pathway. So what will happen to the patient? There will be hypokinetic hypoglycemia, hypokinetic hypoglycemia. There will be seizures, because there will be internal brain activity because of the drop in amount of glucose. There will be coma. The patient will have coma when the oxygen level drops and the body rely on anaerobic glycolysis to occur. What happens? There will be muscle weakness, there will be seizures, there will be coma. The body will go into hypoglycemic coma, which is the patient will faint. Then sudden in infants, there will be sudden infant death in extreme cases. Sudden infant death because you are starving the body of glucose. I get him now. The next one is increase in omega oxidation severely will cause so many issues, because you mostly, like I said, you'll be seeing the dicarboxylic acid in your urine. Are you getting that? They will be seeing it in your urine, and it always caused when there is any of the deficiency in any of the enzyme that is undergoing beta-oxidation. It could be MCAD, it could be carnitine, it could be what, multiple acyl-CoA dehydrogenase deficiency, which is multiple in the sense of there is deficiency in the acyl dehydrogenase of very long chain fatty acid, there is deficiency in what, all chain fatty acid, there is deficiency in long chain fatty acid. All these things will lead to what, omega oxidation. So in recap, now I told you that fatty acid oxidation is the what, oxidation of fatty acid in order to form what, ATP. I get it now. So we want to oxidize fatty acid to form ATP. Naturally, the body knows beta oxidation, because beta oxidation is usually because the body can oxidize palmitic acid very well. The body can oxidize palmitic acid. The body can oxidize medium chain fatty acid. The body can oxidize all chain fatty acid very well, because they'll be forming intermediate of TCA. But the problem is that when the body cannot oxidize these people, the body not depend on what special pathways, which is the alpha oxidation, the omega oxidation, and oxidation of very long chain fatty acid, for the body to what, get through to the day. When there's deficiency in enzyme that goes for beta oxidation, the body will start relying on another thing. So very, very important. So hope it all made sense to you, because we are talking about beta oxidation of all chain fatty acid, beta oxidation of very long chain fatty acid, alpha oxidation of branch chain fatty acid, omega oxidation. We have talked about all these people. Again, I so hope you understand, because I had to play all this video once so that you understand the special pathways of fatty acid oxidation. If you are new to my channel, make sure to subscribe and turn on your post notification button, so at any time I drop any video, you'll be sure to be notified. If you want me to make a video for you, drop it down in the comment section. I promise I'll make the video for you. We'll be going into what, ketone body metabolism, which is ketogenesis and ketolysis. I'll see you in my next video. Bye.